Thanks a lot for the invitation. I just received my pleasure. So this is the right thing. Yes, I take it as a yes. Well, thanks a lot for the introduction. I'm not there. I'm not in Boston currently. Oh, there is a hand up. Is there anything? Emily has a question. Okay. So I was saying I'm not in Boston at the moment. I was traveling for a conference. I'm in Europe, but I'll try to present what we're doing in my group, and feel free to interrupt with questions. So I want to make this very interactive. So as it was said in the introduction, I am a faculty at MIT. I started a couple of years ago, and I'm a part of LEEDS, IDSS, and civil engineering. My group has people coming from all sorts of backgrounds, from applied mathematics to computer science, transportation, operations research, civil engineering. And I could not find a picture where we were not about to have some meal or some dinner or some lunch, or we just had lunch. So we really like to go out and enjoy our lives. So this is a picture of them, and I will mention them when I talk about their particular efforts in our projects.
Gioele,
and I thought of briefly,
Gioele, can I interrupt first, quick second? You're in
Sure.
presenter view, not in the presentation mode. If you want to switch, there we go. Thank you very much.
I asked about this. I wasn't sure about. Sure. I'll show you my students' faces here so that you can see them full screen now. Does this work now? Yes. Good. I don't hear anyone, but I assume it's a yes. Okay. So what does my lab work on? We work on what we call complex system design and operation. What are complex systems? I thought of bringing some examples. So you can think of a complex system such as intermodal mobility systems. So systems that are made of various modes, say autonomous cars, public transit, autonomous drones. And these systems have to be first designed, so you have to choose which technologies to use in which scenario, but also coordinated and controlled in real time. You can think about similar things when you fix a particular technology. I work a lot on autonomous cars, autonomous driving, or you might imagine similar problems happening in large warehouses. For instance, here you see a picture from Amazon Robotics. We also work on similar issues or problems in autonomous maritime shipping. So when you are designing ships that are delivering cargo, but they are doing so in an autonomous fashion. And we have similar application in automotive and soft robotics. Now, what is common to all of these problems is that you have to make a lot of decisions at different levels. And these decisions kind of impact each other in various ways. Right, so here I'm reporting kind of three of the systems we typically care about: city transportation, warehouses, port. And in all of these systems, you have to make decisions about single agents, which means designing the system itself. You know, where do I put sensors? What engine do I use? What particular algorithm I'm using to control the robot or the agent? There are decisions at the fleet level. So how many of these agents should I have? What kind of agents should make a fleet? Or if I'm given a particular task. So also heterogeneity and diversity play a big role here. Then there are decisions about the environment. How do I design the environment on which these systems operate? Like how do I design the roads? How do I design the warehouses, the port? And then there are problems around coordination of these technologies. So how do I simultaneously control and operate all of these systems? And finally, there are also operational choices where you might imagine you have many of these systems now interacting together. How do I coordinate them, right? Now, I want to start with a teaser or a brainstorming that will kind of guide us for the entire lecture with a very specific example. Now, I'm fixing a particular one of these systems. The system is you have a warehouse. And the warehouse is represented here as a rectangle, but bear with me, use a bit your imagination. And now I'm giving you a task. You have to cover a certain area, or in other words, also find some particular object. Think of it as an Easter egg you have to find. And you are given total freedom about what you're going to design. So it could be a fleet of robots. It could be you hire a lot of humans to go around and hunt. Could be that you set cameras around. But what I'm telling you is that you really care about time needed to find this object or to cover this area, energy spent, and the cost, the monetary cost of achieving so. And now I want to find the best solution for this task. And now I want to do an exercise. We do this before I show you the magic to answer this question and after. And I want to see if the answer changes. So right now you have not seen my lecture yet. So who has some ideas about this? I want to hear more from you.
Do you have any in-person thoughts? Virtual? Oh, we have one in person. I'll move over there.
Usually the first one then drives all the other ones, right?
Well, it's kind of a vague idea because we don't have a lot of specifications, but I would assume if, for example, you had a fleet of robots that are capable of like scanning the area, you would probably want to find the limits of their ability to like how much of an area they can scan in time, and then split that the total the warehouse into sectors that are either slightly less or equal to the maximum area that each of the robots you have can scan, and have them each scan like a small section of the warehouse for the object at intermittent times until it's found.
That's a very good answer, actually. Thanks a lot. So there are many pieces of this answer. One is you're saying we're going to go with robots. The other one is we're going to choose robots that are kind of able to cover the order of magnitude of the area that we are dealing with. And then you're also saying we have to design an algorithm that's kind of clever in deciding where the robots are going, right? This is, if I understand correctly, that's your answer. And it's a good answer, right? But not, even if and this is assuming you're using a particular solution, which is robots and a bunch of algorithms. Now, even here, there are a lot of degrees of freedom, right? What robots am I using? Am I using ground robots? Am I using Roomba-like robots? Using drones? Am I using some fancy humanoids from Boston Dynamics? Why? And I mean, the answer is also why would I use some of those robots or not? Or would I use humans in this? Should humans be involved at all? Should I have sensors that are fixed, right? I put some sensors everywhere in the warehouse. We don't know the answer. Don't worry to say something wrong, right? There's no right answer. It's a complicated problem, right? But any other thoughts? I maybe collect another one or two and then I'll move on.
Yeah,
I see someone from the Zoom. Yeah.
We'll take someone from Zoom, and then we have another one in the room as well.
Thank you.
Awesome. Nichiapan, do you want to unmute and answer?
Yeah, sure. I also don't know much about this, but I think something that could be helpful is like a main system that can track the coordinates of all of the different like robots or drones or anything that's in the warehouse, and then it can make sure that the things are like properly spaced so they aren't redundant and like in similar areas, and they're also spaced enough where they can grab items. They can grab items very quickly because they'll be spaced out across the entire warehouse.
Yeah, very good answer. That's also a very good point.
All right, we have one more from the room.
Something you could do is sort of like a cumulative slam where you have a bunch of small like cars or per se, and then all of them sort of run a slam algorithm with LiDAR, and then you have a main server that gets all these sort of slam maps and like adds them and lays them up to make one big cumulative map that all of them can sort of navigate and plan for.
Yeah, very good. This is going deep into the algorithmics. SLAM, I don't know how many of you are familiar with SLAM, simultaneous localization and map. By the way, strong origins from MIT. Almost all the state-of-the-art research is done at MIT currently. I mean, also other places, but MIT is special in this regard. So yeah, exactly. So that would be a solution that mixes well with the first answer, for instance, right? Once you have robots. But now all of these decisions also have to take into account that the warehouse might change, or the technologies might change. You might buy thousands of these robots, and now a year after, they introduce the new technology that is superior. But now you already spent your $1 billion on those robots. What do you do? So for instance, how do you deal with the idea that tasks could evolve over time? You have to buy something now for something that is not necessarily be the scenario of tomorrow. To give you a number, Amazon Robotics currently operates more than 1 million robots globally. So these decisions have a huge impact if you're starting to propagate them in different warehouses. Good, so we'll keep this in mind for the entire talk, and I will show you some ways to solve these kind of problems. But the key message here to start with is that the societal or the implementation of this technology does not only depend on the technology itself, that typically is designed with general applications in mind, but also on it embedding into larger networks. For mobility systems, you can imagine an autonomous car, and then imagine the embedding into a real mobility systems with real regulations, with fleet sizes, and so on. Here, you might always find good arguments for one technology over another, right? You might think, oh, autonomous cars will solve all the problems of the world, or will make mobility more affordable, more sustainable. But on the other hand, you will also find people that tell you, oh, there are also potential bottlenecks or issues with these technologies. What we do in my research group is we don't necessarily care about one or the other side of the spectrum. What we know is slowly understand well single components, right? As people said in the audience, we know well how to think about the reach of a specific robot technology. We know how to design a SLAM algorithm once I chose my robots and I want them to localize themselves. What we don't know is how to make all these components interact. So we lack something that allows you to think about co-design or compositional design of these systems in a formal but also practical way. I will be precise and say what I mean when I say formal and practical, but we want to have something that allows you to write theorems and proofs and know exactly that you have some guarantee that some of the solutions are really the best ones when it comes to optimization, but also you want something practical people in their daily lives can use to make decisions, okay? So the talk today or the lecture is giving you some insights from some of our research projects, and hopefully we'll show you a side of robotics and automation that kind of puts all of these things together in a new way. And I know this is just a lecture and probably you will leave with a lot of questions, and I invite you to send me emails after this talk and ask more, but also you find all the papers and things I mentioned on our website, which is just mylastname.mit.edu. Very good. Okay, so first of all, when I say co-design, what I really mean is thinking about a language to simplify or automate the task of the designer. And I think you guys think a lot about design, especially during this BW initiative. Here, I think about design in terms of minimizing some resource usage that your system is subject to some functionality constraints. Now, if you go back to the example I showed you before, resource usage would be the time needed to cover the area, the cost, and the energy consumption. And the functionality is the task, essentially, that I gave you. I said, oh, there is this warehouse, there is this particular thing you have to do on the warehouse. Now find the best design that does this. So we want to create a language that allows you to specify this task in a way that is useful, take some multi-domain knowledge. So essentially the knowledge you guys have, which the few of you answers have, and now take some design options or some possibilities to solve this problem. And now some magic has to happen and some optimal designs have to come out. So let's be concrete. For the autonomous cars, tasks could be distributions of scenarios or situations a car will encounter in their lifetime. The principles might be principles from robot autonomy and physics, right? Stuff people study for these technologies. And now the things you are designing are the components, right? Sure, there is a car, but how many sensors? Which sensors? Where do I place them? How do I operate them over time? And what about the algorithms? And now the optimal solutions are in terms of the trade-offs, right? So for instance, you might look at energy versus error, right? And now, since I have two costs I care about, I will have a trade-off. There's not a single solution. There are a bunch of solutions that are not comparable with each other. If I think about mobility, there might be a very similar problem, just with different details. Now, the task is to serve demand in a city like Boston. You have a bunch of people that want to travel from A to B. The things you are the principles you are using to design your system is networks, operating infrastructure. And now the things you are designing are the mobility services themselves or the policies the municipality uses. And now this might be performance versus investment, right? Now, why is it hard to come up with this magic? Why is it hard to design or to formalize design? I think everyone in that room, even the virtual and both the virtual and the physical room, you guys have a notion of what it means to design something, but it's very hard to formalize this task. I give you essentially three reasons that motivate me. One is designing these complex systems requires making decisions at different levels that influence each other. I take the example of autonomy. To design an autonomous car or a fleet of autonomous cars, you need to design hardware, software. Software is not a single thing, but it's sensing, control, perception, communication. Some things are not even hardware or software, right? You have liability, regulations. And the typical reaction if you are a systems engineer is to picture yourself at a therapy session where you say, oh my God, I don't know even how to deal with these systems. There are too many objectives, too many components, and I'm not even able to understand the whole thing. And importantly, we forget why we made choices, right? You enter a company and there are choices that have been made in the last century, but nobody knows why. Nobody knows what really is happening there. And therefore you are afraid of making changes because you're afraid of breaking the thing. So the diagnosis of the sickness is that we lack a toolbox, which is formal, quantitative, but also intellectually tractable, something that people can use in their daily lives to design and operate these systems. So first challenge is many components, many decisions, and these components and decisions kind of interact together in a weird way. The second challenge is that not only you have many components, but all of these components kind of embed into each other in a vertical way as well, right? You might design sensors and you care about sensors only, but one day those sensors will be used on a car together with many other components. And now you might be an expert of designing the car itself, but now this car only makes sense if it's embedded in service where you have many cars that serve mobility demand and they have to be coordinated efficiently. Now, these services only make sense if they are embedded in a clever way into larger infrastructure planning, right? Now, you might zoom out and even think about mobility and energy networks interacting together, or you might zoom down and think of designing the next NVIDIA chip that powers all of this compute, right? So a lot of decisions at the horizontal level, but also the vertical level. Now, the third layer of complexity comes from the fact that you cannot make decisions about all of these systems together, right? You sometimes have to come to pacts with other people, and sometimes these other people have totally different languages to talk about the same problem. That's a first challenge. And the second challenge is people care about different objectives. So there's not a single best solution, but there is a compromise, right? And you have to find the trade-off. So in summary, just what I just said is you have large components, a lot of components, many scales, different natures of modeling techniques to think about the components, and a lot of objectives. And on the other end, you might have many agents that interact with the system, both in a collaborative but also conflicting way. So this is a very hard set of problems. And when PhD students start in my group, these are the 6 golden rules I give them for a framework that deals with this. Right? Ideally, if we design something that solves these problems, it satisfies these 6 properties. The first one is it's a framework that allows you to be precise when you talk about all of these things. It has to be a formal, domain-independent framework, something you can write math about. You can be very precise about. Then it needs to lead to some problems you can solve. It needs to be computationally feasible, right? It does not have to live in theory land, but you need to be able to do something with it. It has to be, you have to be able to model these horizontal and vertical dependencies I just talked about. which means compositional. It needs to allow you to do vertical and horizontal composition. I also want this to be collaborative, meaning people in this room need to be able to pool knowledge and reason about this together. But in order to achieve that, it also needs to be intellectually tractable, meaning we need to be able to contribute to the design without understanding everything. Sometimes when you go to big companies, you will realize there are the so-called system architects. Those are super clever people that know everything about every little detail of the system. And now the way for people to contribute to the system is to interface with this person. I want this to be kind of a distributed exercise where everybody can contribute in a way that is accessible. And finally, continuous, adaptive. We need to be able to continuously change our design decisions over time if things change. Good. So today I will zoom in some of these problems, and I will mainly focus on the first layer of challenges. The second layer of challenges is very cool. I have a separate talk about it. Maybe I will give it another year. But I think this first one is very, very good for this particular audience. And what I will present to you is our framework for co-design, where co is branding for collaborative, computational, compositional, and continuous. So this is why it's called co-design. I will try to hide some of the math in the background. So it uses some tools from something called domain theory, applied category theory, and optimization. But don't worry, you don't need to know anything about this to understand this. But I want to give you a better sense of what these problems are, how you can model them, and how solutions look like. So by the end of this talk, you will understand these weird diagrams you find in my paper, the ones you see on the left. And you will understand how to go from those diagrams that represent design decisions for systems to actual trade-offs or solutions in case of a particular task you want to solve. And now, here is some advertising. I think Autonomy talks were already advertised. I'm very glad this happened. But here is a second page. If you like this stuff I'm talking about, I'm publishing a book with Cambridge University Press on this subject. You find the PDF already online. And this book assumes zero prior knowledge. So any student can start and learn this. And we're also teaching a class at MIT about this stuff, open to both undergraduates and graduate students. Good. The first concept to learn or to understand is to think about design in terms of three spaces. You think about designing a system or choosing components when you design a system. You first want to know the implementations or the actual choices. Those could be parameters of your algorithm. It could be which sensors you are mounting, the shape of the chassis. All these decisions come at a cost. They come at what I call resources or cost. And they typically provide some specification or functionality to the system, right? And you might know these things, right? Functionalities are behaviors, specifications, objectives, guarantees, and resources instead are budgets, requirements, and dependencies. Now, the key thing there is a question from Siriam. Was it a mistake, or do you have a question?
That was an accident.
Okay, no problem. Feel free to stop me for questions, right? I'll try to make this. I know this can get out of control with over 500 people, but we'll manage. We solve complex systems, so we'll manage. So, all right, so the key thing to understand here is that we want to be quantitative when talking about these pieces, functionalities, resources, and implementation. I typically think about requirements or costs as minimized. That's why you would see these in red in the slides. And I think about functionalities as something I want to maximize. That's why you will see these in green. And I will typically look at trade-offs. Now, I know maybe you're not used to thinking about trade-offs, but I will show you today a lot of these plots where you're maybe even comparing two costs and you have a curve. Everything above this curve possible is feasible, but it's not minimal if you're trying to minimize these two costs. Everything below is a dream, but you cannot achieve it. And everything on the curve is the so-called Pareto front, or is the best thing you can do, right? Imagine this morning when you were going to MIT, you were thinking about cost versus time needed to get to the event, right? Monetary cost and time. There is a solution which is you just walk, it's free, it's gonna take some time. There is a solution which is get a very expensive Uber Black, And depending on where you are, it might get you there faster. So those two solutions are technically not comparable if you think about those two costs, and those form Pareto fraud or an uncomparable set of solutions. The same goes with functionalities or mix of functionalities and costs. Now, since this is a kind of a strange thing, I remember when I was your age, I wasn't thinking about trade-offs in this way. I want to bring you some examples. So a nice example is this one of speed versus strength for the human body. Those are two athletes. Usain Bolt, famous for being very fast, not necessarily very strong. Oleksiy Novikov, famous for being very strong, not necessarily very fast. Now, they are both, if you look at this plot, much faster and stronger than me. I think this very bad and dominated spot on the bottom left. But there is this trade-off of the human body. The example that we use in my class to teach this concept is this one of functionalities and resources when it comes to face masks. Unfortunately, we know something about these masks. I feel we all learned a bit what these masks mean. And if you just have a functionality that protects the wearer from a virus, you have kind of a total order, or you can always have one that covers more than another one, right? You have a fashion mask, which is the bare minimum, surgical masks, and then there are these fancy codes, FFP1, P2, P3. Now, this is true if I just consider one function, which is protecting you from COVID. What about you considering two, right? There is one which is protects somebody from COVID and says something about the wearer. It gives you information about the wearer or what the wearer cares about. This is totally arbitrary, right? We can argue about how to order things, but the fashion mask, if there is a strong virus, tells me some people like to have style, not necessarily care about their health. Or the super strong FFP3 tells me somebody really cares about being protected, right? So there are these statements. There are also scientific statements about protects the wearer and protects others. You know, there is these two directions of protection. Or you can also order them by price and functionality. Now, if you notice, all I'm doing is changing the cost and the axis, but this is changing where things are positioned. So you realize that understanding this axis is very important when you make design decisions, because these design decisions depend on what you care about. Another example is headphones, right? You can have a functionality that's very important in Boston, keeping you warm, and another which is music reproduction fidelity. There are two that keep you warm and do not reproduce music. There are some that kind of reproduce music pretty well, but don't keep you warm. And then there are some that could keep you warm and reproduce music and like have this strange mix of properties, right? You wouldn't buy these headphones if it was only to keep you warm, but if you care about these two things equally, now you might consider buying these headphones, right? If you now care about price, now the story changes, right? Because now, for instance, these headphones that can keep you warm and reproduce music are also very expensive compared to the other ones, right? So now suddenly this does not make that much sense anymore. If you, for instance, care about frequency of charging of these technologies, now you might have other headphones that are not necessarily preferred over one another. So I hope this, I think I had another one, hassle of dealing with wires. This is another one that some people don't like wires. So all of these things are very important when designing a product. There is though a law, the law of successful products, that says at equilibrium in an efficient and free market, no product should completely dominate another one by functionality and cost. In other words, if a product exists, it means there is some set of functionalities resources in our formalism which somebody might buy, right? Okay, so I'm Swiss. I decided now to bring an example of functionalities, resources, and implementations. And since I'm Swiss, I could talk either about watches or chocolate, right? So I chose watches. And so let's start with an example in which you have two implementations. One is a Casio F91W, and another one is a Patek Philippe. Now, asking it to the audience, what do you think might be a resource or a cost for this product or for these implementations? What could be something I consider as the space of resources? Chase as an idea.
The materials needed to make these watches.
Yes, yes. But that's a very good one. So I cannot adapt the slides in real time, so I will not have exactly the spaces you guys mentioned, but your name suggests another one, a simple one. Your first name suggests that, right? Could be the basic cost I have to pay for. Money, right? Expense, whether something is expensive or not. Sai, another point, maybe?
I was gonna ask if the labor cost was one that could be
Labor
used.
cost could be one, exactly. Whether it costs more to produce it or not. For now, I have a very simple price, right? Price of this product. One costs a lot, one costs much less. Let's not go into detail of how much, but you might have labor cost, you might have energy cost, you might have transportation time, whether some materials are available or not. You might have robustness of the supply chain, right? The Patek Philippe produced in a very small country, a very small town in Switzerland. Casio F91Ws are produced around the world. All right, so we have a lot of this cost. Good. What about functionalities? Why would somebody buy such a watch? What is the utility of a watch?
We have
What
a
do you think that
couple
could be?
answers here in person.
Sure.
How well it tells the time, like how easy it is to comprehend what the watch says.
Perfect. You read my mind. This is what I call watchiness. So one tells time and allows you to set multiple alarms. That's the Casio. And another one tells the time. That's it. So far, do we want maybe to get another answer? I don't have another. The animation is this one, but maybe we want to collect.
Yeah, we have one more here.
Yeah.
Another one would probably be like the social implications and social standings of a watch. Like, obviously, an analog watch is a lot easier to read than obviously a digital watch is a lot easier to read than an analog watch. But a lot of but people still buy Rolexes and stuff, sort of as a social standing, rather than like a functionality piece.
Totally agree with you, and you're reading my mind, right? Again, because think about this. So far, I was showing you resources and functionalities, and I just told you. There should never be a case, if I want to minimize resources and maximize functionalities, there should never be a dominated case as a product, right? Because it would mean nobody would buy it. Here, if you notice, Patek Philippe is very expensive, but has less functionality. If I were to just consider these two things, it has less functionality than a Casio F91W, right? So why would a Patek Philippe exist? And there is one other aspect, for instance, which is what your colleague said, which is signaling. Whatever that means. I have somebody who can afford a Patek Philippe, for instance, and I chose to buy one. The signaling for the Casio, I don't know what that could be, but trust me, on MIT campus, we will find a lot of people that like Casio for its simplicity, and we don't really care about the Patek Philippe. So this is just to say, this is a very simple example, but it's just to say every system you design has functionality as a resource, and you have to make design decisions that are very complicated, but all these design decisions eventually depend on products, right? And choosing wisely or thinking carefully about this will have an impact. Now, how we model this is through the so-called partially ordered sets. You can model this notion of having preferences about things with this mathematical structure. This is something that allows you to model classic things where you can always tell that something is preferred over something else, right? For instance, real numbers, positive real numbers. I can always say that one number is larger or equal than the other one, right? I can always say that 10 watts is more than 9.9 watts, for instance. Or natural numbers. I can always count the cars parked in the MIT parking lot and ask whether it's more, less, or the same as the day before. Partial sets also allow you to say that some things are not comparable, exactly as we had before for speed versus time when coming to MIT. So they allow you this extra degree of, and for instance, since you're in Boston, you might like lobsters more than lobster roll and lobster bisque or clam chowder, and you really don't prefer one over another. So you have this free degree of freedom that you can keep in your system. Another similar one that we use in our research is this idea of ranking different trajectories for an autonomous vehicle. Here you see there are a bunch of trajectories. And now you might care about different things. You might care about the energy for your collision, the area violation and the clearance. And now you prefer collision over everything else because you want to be safe. But then you might have to violate the area or the other lane for some reason, or you might have to keep a distance to obstacles. That's called clearance, but you don't really prefer one over the other. And this thing has an effect on the trajectories, right? Now, if you have to choose trajectories based on this preference, you have to rank these trajectories. And for instance, here you might say, look, the trajectory A is the worst of all. It's colliding into the cow, right? So it's a very bad trajectory because I care a lot about collision. So that's going to be at the bottom of my choices. I will never want to choose that. Now, when it comes to the other ones, I have two options, right? There is trajectories B and C that are kind of close to the obstacle, not into the obstacle, but do not violate the lane constraints. So they don't go to the other lane. On the other hand, D keeps a very large distance from the obstacle, but violates the lane. And so these two are not comparable, right? So this is an example of how partial orders play a role in motion planning or trajectories selection. If you know something about decision-making under uncertainty or machine learning or estimation, sometimes you represent uncertainty with positive definite matrices or ellipsoids. And now you can represent more uncertain or less uncertain things by representing ellipsoid inside ellipsoids. If one ellipsoid is inside the other one, now you can talk about a dominated case in terms of uncertainty. The thing to share with you is that we think about functionalities and resources as partially ordered sets, so we'll be able to specify those. And now you will think about functionalities as something to maximize for a system, and as resources as something to minimize. Now comes the first and only equation of this talk. I tried to remove all equations and to make it very intuitive, but this one I kind of have to give you. Now, the notion of solving a design problem is the one of answering this question. Given a functionality I want for my system, and given a resource I have available, or a bunch of resources I have available, does there exist a design or an implementation that gives me at least what I want by requiring at most what I have? Okay? This is what this equation is saying. So given a particular watchiness and signaling I care about, and given some money I have in my account, does there exist a watch that gives me the watchiness and the signaling by costing at most what I have in my bank account? Okay? This is what's called a Boolean profunctor, and it's a box for me. It's something I will draw with functionalities on the left and resources on the right. And now you might say, okay, but this is a math formula. What do I do with this? It sounds very counterintuitive. But in practice, you have many ways of coming up with these relations or these design decisions, right? Sometimes you have catalogs of components you can order from the internet, and these components have some properties, right? For instance, a drone has some weight, some price, the properties of the camera, and some fall naturally into functionalities and resources. Sometimes you have things that are independent of the technology, right? The energy for a mission and it's always greater equal if you're designing at home than the duration of the mission and the power consumptions multiplied. Or if you're running experiments or you're solving problems or you're running simulations, you will have a bunch of these points, and these points will deliver some notion of feasibility. Now, I think a very nice exercise for you would be to, at the end of this talk, go back where you like in life, not even in research, in life, and draw a box like this one. And I'm pretty sure you would be able to find a box of this kind. As I said, I'm Swiss, I can produce papers if you give me chocolate. Here I'm talking about quantity, not quality. But you name it, right? We have all sorts of things. If we go back to the initial slides, you could have a swarm of drones to design. The area to cover is a functionality, but now the things you are paying are the resources, such as the speed of each agent, the number of agents, the time needed for the agents to cover that area, or the total. If you are into optimization, you can see resources as constraints and objectives as functionalities. So this is to say this is a very universal language to think about components. But now, in all of what I said today, I'm thinking about many components interacting together. And I guess you realize that these have wires. And now what I want to do is take these wires and interconnect things. So there is a theory we developed that shows that you can take any of these boxes, compose them in various ways, and now the result of the composition is again a box. So the property of being a box is compositional, meaning I can reason about it in the same way as I did before. And you can do this at the graphical level because we have very powerful mathematics in the background that kind of checks whether this is feasible or not. I can put two things in parallel, like I'm saying, hey, I provide something to you, now you use that something to create something else, right? I'm a chip, I produce computation. Computation can be used by an algorithm to produce some results. I can put things in parallel if two things are happening in parallel. I can have a feedback operator. I can try to put together different components and be robust to both, or try to choose the best component. And whatever I do, it's again a design problem or a box. And this is becoming very important when it comes to taking a very large system and decomposing it into the subcomponents. Now, when I say feedback, I think I wanted to stress this because I think you're encountering this in your daily design tasks. When I talk about feedback, I talk about the complexity of designing things. Imagine designing a drone that requires an actuator. This actuator must be powered by a battery, and the battery must be carried by the drone. Now, the heavier the drone, the more power you will need, and the more actuation you will need. But the more actuation you will need, the more power you will need, and so on and so forth. So you have these recurring constraints that make the problem hard to solve, right? This is where the feedback lies. But you can also think about it in terms of you have an engineering problem, a business case, and now you want to find the best solution. So just out of curiosity, how much time do I have left? Because I want to leave some space for questions.
10 more minutes.
10 more minutes, fantastic. I can make some points. So
10 to 15 minutes.
10 to 15 minutes, great. So the mathematics we are using in the background, it's called applied category theory. And maybe right now, you've never heard of it. It's kind of, not on your radar. It will soon be, trust me, but I want to quickly talk about what it is. What is this magic? And think about all the math you know as a set of patterns to describe the world, right? It could be differential equations, it could be some models you're using to design a drone, whatever. It's a set of patterns to describe the world. The issue is that the engineers of the 21st century have to deal with systems that are made of many components, complex architectures, and a lot of interactions. Applied category theory is a set of tools that allows you to talk about these compositions in a formal way. Category theory was initially designed to think about how to transfer results between different parts of mathematics. And now applied category theory kind of tries to find applications of this concept. So I will tell you what it does for you and what it doesn't do for you. What it does for you is it creates a library of reusable concepts and also visual language. These diagrams you see here are actual diagrams that represent some very precise mathematical concepts, but they're very easy to play with, right? You can move around the boxes and so on. And when you move around things, you're doing something, the mathematical world behind, but this something works automatically. So they facilitate your interaction with the system. And these boxes could represent steps in a plan, they could represent very complex systems interacting together, or they might even represent different cities and transportation networks. What it does for you is solve the problems. So we develop a lot of this math to formulate the problem well. And now, once you have formulated it well, you can solve them in a more efficient way or in a better way. And everything I'm talking about today arises from this domain of mathematics. Now, long story short, before us, this toolbox was almost exclusively taught to mathematicians, and computer science is developing new programming languages. And there was no book for engineers or designers, or essentially there was no book that was easy to read. When I started learning this stuff, I read like 5 or 6 books, and after the 6th, maybe I started understanding something. So what we did was writing a book exactly for this use case, for people like us, engineers, that want to learn this mathematics stuff, but with a very applied taste. And that's the book you can find on my website, and I invite you to read. Now, if you want to see other applications beyond what I showed you today, there are many exciting areas, right? This is a collaboration with Markus Bühler, another MIT professor that works on many things, among which intelligent materials, that was led by Lee Marom. And they created with category theory, a framework to go automatically from observing some natural materials, pine cone, and automatically creating instructions for a 3D printer to print the same exact material with the same exact dynamical properties, right? Way that preserves the exact nature of the original material. With Vincent, my PhD student, we are working on using category theory to create a representation to talk about deep learning architecture design. Probably all of you on a daily basis ask your favorite LLM some question, ChatGPT, Claude, whatever. And a lot of these architectures are designed with something in mind, but in a very ad hoc way. And now we're trying to formalize these design decisions using category theory. Now, I want to use the last few minutes to show you what it means to solve these problems and show you some case studies. So when I talk about solving these problems, I think about fixing the behavior I want from my system and minimize resources, or given the resources I have available, finding the maximum functionalities. So in other words, think of watch example. I fix the kind of functionality I want, and I try to spend as little as possible. Or I fix the money I have in the bank and try to buy the best watch I can, right? This is the question. These are two dual problems. In practice, what we care about is finding a map from the set of functionalities to these minimal resources. Now, I don't want to bore you, but this is a very complicated optimization problem that no one has seen before. If you know something about optimization, it doesn't have the classic properties it should have. So typically, the result is, as a researcher, you go to bed, you wake up the morning after, and you change problem, because this is too bad. However, we were very happy to solve this problem in a kind of efficient way by exploiting these compositional structures. So you can prove a theorem that tells you that you can solve the composition of different problems, but just solving each problem separately and then compose their solutions. So in a way, you can decompose this whole huge optimization problem in an efficient way. And you can create an algorithm that gives you all the optimal solutions, so all the solutions you care about, and this algorithm does not explode with the number of options you have available. So this is very cool to know. And the other important thing to know is that you don't need to learn anything about what I just said to use this stuff. So there is a language that we are developing through which you can specify these problems. And then there is a solver that allows you to solve these problems efficiently. And now I want to show you kind of some examples. So let me go to the examples in the interest of time. So if we start with the idea of designing an autonomous vehicle, you want to think about all of these different components and how they interact together. And when you do that, you end up with these diagrams you see here. And now how you think about feasible options for each box depends on the domain, right? For computing, it's a catalog of computers. You can think a set of NVIDIA chips. If you think about control, it's about simulating or optimizing what the system might do with different control actions. If you think about perception, it's about testing what sensors might do in which conditions. For each boxes, you create some options. And then what happens is you ask some questions. For instance, in the context of autonomy, you fix some desired scenarios you want to traverse. And now what this framework I just presented does gives you some optimal solutions, or solutions that try to minimize resources. For instance, error versus cost, or error versus efforts. And for each point on this front, you can extract the actual design solutions, like which controller you used, which sensor, which computer, which parameters in the algorithm, and so on. And now if you make the tasks harder and harder, you can visualize the hardness of the task as the resources that are required that increase. And now this is a toy example, but we are doing this at the level of real autonomy stacks with cars such as the ones you might see in San Francisco, such as Waymo and so on, where now you can decide to place sensors, how to operate them over time, and so on. Now, we are doing this at the same time, also very large systems, where now you might want to design an entire mobility system, all the way from public transit to micro-mobility options to fleets of autonomous cars that serve passengers, right? And you want to design the options, the fleets, but also the networks on which these fleets operate. So for instance, on which roads should which technology operate. Again, this is a co-design problem. You can use the very same theory. And now the kind of answers you can get are the kind, maybe I want the travel time in the city as a metric for any origin destination pair. So for any trip request, I want to measure the travel time, and then I want to measure the average. And now I want to compare this with the investment I have to put into the system. And now I have a curve where every solution is the type of vehicles I should use, the number of vehicles, the network on which they should operate, the number of trains, the number of e-scooters, and so on and so forth. So this is like a very big system, and you're able to give some options to these people sitting at the stakeholders table to make decisions. And we have a lot of projects ongoing with Sidara and the Department of Energy to scale this to entire cities and analysis for the entire cities. It was a case study for Washington, D.C., but now we are trying on many different cities in the world. And the plan is to do co-design of everything. So we have a lot of open projects working with different companies and institutions to apply these tools. And one I'm very excited about that connects to the first problem I showed you is this new center for compositional optimization we are launching at MIT together with a bunch of companies and a bunch of colleagues, among which Ali Jadbabaye, that you see on the bottom left, who is the department head at civil engineering. And this project is exactly about what I talked about before. So you have a task, you have a bunch of technologies, in this case it's different robots, and now you want to choose some metrics you care about and design the best technology for that particular. And going back to the problem I told you before, you kind of already gave me some answers, right? And I was very surprised by the quality of the answers, so you should be proud of yourselves. But it's exactly what some of you said, right? You have to cover a certain area, you have to design a fleet, you care about a bunch of objectives, and now you have to co-design everything. The fleet size, what is in the fleet? Is it sensors? Is it robots? Is it sensors, robots, and humans? For each robot, how do I design the robot? What are the batteries I should choose? What are the sensing decisions? What are the perception modules? And the planners might look like these planners here you see on the slide, right? Different ways to allocate tasks. You can model these as a bunch of boxes in my language. So you can see these boxes here. And this is exactly the same as I presented before. And then you can extract optimal solutions. So if you care about the questions I said before, for instance, cost versus time, you can produce this Pareto front where now I model these in thousands of US dollars to buy the fleet and the time needed to cover the area. As you see, there are solutions that take a long time, almost 2,000 seconds. There are solutions that take as little as maybe 200 seconds and everything in between. And now for each point, I can tell you exactly which robots I'm using, what kind of designs for each robot I have, kind of coordination algorithm, right? There might be some coordination algorithms that are very stupid and cost less energy. There might be some that are very expensive to compute, and you have all these trade-offs, right? You can also start visualizing trade-offs in terms of heterogeneous versus homogeneous fleets. You can show the value of having fleets made of different types of robots that deal with different kinds of situations, which I think is very interesting. And you can also start building and access roadside assistance.
Hi everyone, I'm Natalie. I'm an incoming freshman at Stanford University, and I was accepted into 7 out of the 9 schools that I applied to.
Can we mute that?
I don't want to mute Natalie. That was not supposed to happen. Or if you have a question, please go. Anyways, so another thing that you can model is decision under uncertainty, right? You might not exactly know.
Guys, settle down. Hey, room, settle down. Thank you.
So there are situations in which you have different tasks and you have to buy your fleet before you know the tasks. Here you can model these things. Now, I'm closing this slide. The very same thing we are doing here, we're doing with a bunch of other case studies. In Amazon, with Amazon Robotics, we are designing the warehouse together with the robots, together with the algorithms. With the port of Singapore, it's a new port they're designing by 2050. We're designing the layout of the port together with the operations, the processes through which the ships will enter the port, and so on. With this automotive company, Ferrari, we are designing race cars strategies to allocate energy to various laps in order to win a championship. And with SD Gatri, which is this company that does large-scale harvesting, we are designing the plantation together with the technology that does the harvesting. So the layout of the plantation with the harvest. And all of these problems are of this kind. And all of these problems follow the same I presented before. So I think this is a good slide to stop, and I'll take maybe a few questions.
We'll do.
Again, the final slides so that you can see the website, which is very interesting. Yeah, so we'll go about this. I see some questions on Zoom, I see some questions on...
All right, we'll do one question, and then we're going to move to T-shirt presentations because we're running a little low on time. So, Anissa, do you want to ask your question?
Yeah, so thank you for presenting to us today. I really liked your point that every system is a part of a bigger system, and it made me think about how engineers have to consider whether something works and then also consider how it fits into everything else around it. So that leads me to my question: how do engineers make sure that a design optimized at a component or vehicle level will still work efficiently and equitably once it is integrated into a citywide transportation system?
That's a very good question. I'm glad you like that point. So the short answer is, as of now, there is no existing framework that can show you this. With our framework, you can do this. You can actually test whether an improvement at the local level can have an improvement at the global scale. So you can imagine all of the case studies I showed you as benchmarks, where now different people could contribute on different parts of the world, and they have a system-level perspective on whether what they're doing locally is improving the system level. For instance, I'll give you an example very quickly. This city-level design I was talking about before. Now, a company might decide to invest $100 million in making the chassis of the car faster and better for some reason, right? That investment would be totally useless if you start considering average travel time and city-level investment at the mobility scale, right? So that if you try to upload models for new cars that have better chassis, now suddenly that is clearly dominated at the system level. Like, you can visualize this. If you instead are in Formula One, these kind of decisions make a huge difference, right? So now different contexts and different models might give you different answers. But this is a great question, and I think there's a lot of research to do around this topic.
Yep, thank you for answering my question.
Yeah, that was a great question. Thank you. Right now, we're going to move on to our virtual T-shirt presenters. So if we could have our two students from Remote Sensing Disaster Response, that would be great. You two can unmute yourselves.
Hi, Dr. Zardini. My name is Advika, and I'm a student in the Remote Sensing for Disaster Response course. Thank you so much for taking the time to give such an interesting presentation. I especially liked how you explained breaking a large problem down into smaller components to identify specific trade-offs, and then how to integrate and optimize all these parts. And the algorithms you went into to finding these optimal solutions to these issues were also really cool. So thank you again.
Thank you, Advika.
My name is Yogi, and I'm also part of the Remote Sensing for Disaster Response course. And I want to thank you for taking the time out of your busy schedule to talk to us. I really enjoyed learning about all the different layers and the different choices that go into a complex system, as well as the 6 frameworks you mentioned that we should always keep in mind. And I really like these because of just how applicable they are. And so, as a thank you, we would like to present you with the Beaverworks Summer Institute 10th Anniversary T-shirt.
Amazing. Thanks a lot. I look forward to wearing it. I will be back to next week. I'll collect it in my office. Thanks a lot. And thank you all for coming here. So get my website, get my email. Don't worry about reaching out and enjoy your time in Boston.
All right, thank you so much. That was our last lunchtime seminar, so we really appreciate it. Virtual students who stay on. All right, guys. All right, so this weekend is your guys' final event. Saturday is going to be the in-person final event, and then Sunday is the virtual final event. So virtual students, if you're local to the Massachusetts area and you want to come into Cambridge, it's going to be at the Johnson Ice Rink. So you guys are welcome to come in on Saturday if you're local and you want to attend. Also, everyone please wear their Beaverworks t-shirts. So Saturday, in-person students wear your shirts, and then Sunday, virtual students wear your shirts, please. Virtual students, that's all I have for you. I wish you the best of luck. You guys can sign off.
Thank you.